Having discussed oscillations, in this lecture we want to start with waves. So, let us first understand what is a wave. So, question we raise is what is a wave? Is it particles moving from one place to the other? So, let us ask that question. Is it particles moving from one place to another? Let us explore that. So, you have seen waves like in an ocean, or if you take a big pan like a thali or something, right, and fill it with water and dip your finger in it. So, I am dipping my finger here. What you will see is that the water goes up here, comes down, and this thing, this ripple, let me give it a name, ripple, travels down, it travels. Does it take water along with it? And we have seen it does not. So, only thing that travels is that ripple, and we call it a wave. When I am speaking to you or anybody across the room, I create a disturbance here. Does it mean that the air goes from one place to the other? If you stand in front of the person speaking, you do not feel any air coming, but you do hear him. So, what happens? Whatever disturbances the person creates travels to your ear. So, when a person is speaking to another person, sound travels, but the air in between does not. So, certainly wave is not movement of a material from one place to the other. So, let us write that a wave does not represent movement of particles. Then what is it? So, the question again arises, what is a wave? And in simple terms, what I am going to say is wave, a wave is a disturbance in any form. I mean, when I am speaking to you, I am creating a disturbance in the air here, and it travels to the mic. From there it gets recorded, or if somebody is speaking to you, that person is creating a disturbance in the air, and that disturbance travels to you. So, wave is a disturbance that travels. From one place to another. But you have heard of standing waves, right. So, question next one is, does a wave mean that the disturbance has to travel from one place to another? So, this is another question, and let me try to answer that. Suppose I have a string, I tie it at one end and give a disturbance here, give it a jerk. So, what you will see is that this jerk or disturbance travels down the string. So, with time it travels. This is certainly a traveling wave, but think of this, I tie this string between two ends and start shaking it. You see that it gets distorted like this and then comes down. So, it is moving up and down like this. what we call a standing wave. And in this wave, the disturbance is not traveling. So, a wave could be a standing wave or a traveling, or what we call a progressive wave. Or traveling wave. So, what we have answered now is a wave is a disturbance created at one place and traveling to another place, what I will call the traveling waves, or it could be an extended disturbance like the string, and which I will call the stationary wave. And now I want to describe it quantitatively. We want to see how really do we describe a wave. So, what we want to see is how do we describe a wave. I will be very general in this, because what you have probably heard in your classes is a wave looks like this and it is traveling. So, what you have seen is a disturbance y x t equals a sine 2 pi x over lambda minus frequency f t, this kind of wave, or it can also be written in cosine terms, a cosine of 2 pi x over lambda minus f t, and then you are told that speed is v equals f times lambda, where lambda is the wavelength and f is the frequency. This is a very particular kind of wave, we will come to it. But before that, since I called a wave is a traveling disturbance, let me come to describe that first. So, let us say I have a string, or as the example we gave is a water surface, and I create, let us say, a disturbance like this out here, or I create a disturbance like this out here, and it travels. To understand it properly, let me say that the disturbance I create is something like this at t equal to 0, a parabolic one. So, let us say this is at time t equal to 0, and the function f, this is function f, this is x direction. So, function f x, or since I am going to later write y, let me say y as a function of x looks like a square minus x square. So, what does it represent? It represents at x equal to 0, the height is a, and it becomes 0 at x equals plus a or minus a, for mod x less than equal to a, and it is 0 otherwise. Just to give you a feeling for the pulse that we have created. So, this could also be a disturbance that has been created on the surface of water. Now, this disturbance travels, and let us say it has gone towards the right and has come at a point where the peak is at x 0. Then the same disturbance at a later time. So, let us say this has taken time t. So, at time t this disturbance would be given as a square minus x naught square for mod x minus x 0 being less than equal to a and 0 otherwise. So, what we have done is either on the surface of water on a string we created a disturbance and at a later time it moved to this point x naught, and obviously if it travels with speed v, this distance x naught is going to be v t. And here it was given as y x equals a square minus x square for mod x less than equal to a 0 otherwise, and on the right hand side I am going to write this is in red. Y x at time t is given as a square minus x 0 square for mod x minus x 0 being less than equal to a and 0 otherwise, which can also be written as a square minus x minus v t square for mod x minus v t less than equal to a and 0 otherwise. What about the case where it travelled to the left? So, suppose it was at x equal to 0 and it travelled to the left. If it travelled to the left, then y x t you can easily see is going to be a square minus x plus v t whole square for x plus v t less than equal to a and 0 otherwise, because now this distance is going to be minus v t. So, what you see in both the cases that the disturbance y x t is a function of either x minus v t or x plus v t. Let us understand that. So, I will make x equal to 0 right here in the middle, create some disturbance. Now, I am not even going to say it like a square minus x, but it is f x at t equal to 0. Then what would happen if it is travelling to the right in time t? This disturbance is going to be given by f x minus v t t equal to 0. Why? Because now whatever disturbance is at time t, which I am going to call f x t, is the same disturbance that was at x minus v t, which was centered around x minus v t at t equal to 0. If on the other hand it travelled to the left, then the peak to peak distance would again be v t. So, whatever disturbance is at t as a function of x is the same as that which was at x plus v t at t equal to 0. T equal to 0 is fixed. So, what we have shown is that any disturbance created at t equal to 0 around the origin, it could be any shape if it travels with a constant speed v and undistorted. So, let me write this. So, a disturbance created as f x at time t equal to 0 will be changing or will be given as a function of time as f x t equals f x minus v t at t equal to 0 if it travels to the right, right means positive x axis, and it will be given as f x t equals the function, same function x plus v t, t equal to 0 if it travels to the left, because that is where it was. Now, that is where it was at t equal to 0. So, a disturbance which has been created at t equal to 0, and disturbance I am calling f x, it could be any disturbance, would appear as, to the right I am going to write f x minus v t, t equal to 0 equals f x t. To the left I am going to write f x plus v t comma 0 equals f x t. This has travelled this way, the green one has travelled to the right. And under what conditions? So, conditions are the disturbance travels undistorted, number 1. Number 2, travels with constant speed v. So, two conditions, it travels undistorted, what is also called, so undistorted also implies what is called in technical term dispersionless. You will hear this term quite often during the discussion on waves. So, it is a dispersionless travel, it does not disperse, it does not change shape, it is undistorted and it travels with constant speed v. You can make out that undistorted assumption is really pretty okay. When I speak to some person, whether the person is standing at 10 meters from me or 100 meters from me or 200 meters from me, if he hears me or if she hears me, what all these 3 persons standing at different distances here is the same word that I have spoken with the same interval, and that means whatever disturbance I created goes pretty much undistorted. So, it is a pretty reasonable assumption. There are cases in advanced courses you will see where there is dispersion. One very obvious example of dispersion is the light wave, where the speed is different for different frequencies, and that is why you see a prism giving you different colors, because the refractive index differs. But right now we will assume is dispersionless travel. So, that is one way of looking at it, that is a function of x minus v t or x plus v t. Another way of looking at the wave travel, another is that if I am looking at a disturbance at certain point x, then what I see exactly what happened at t minus x over v at time. Okay. Another way of looking at the phenomena is, wave phenomena is, let me suppose I am standing at a point x and see a disturbance here. This disturbance would have taken time t equals delta t equals x over v to travel from the origin. This time taken is x over v. So, I can safely say that if I observe a disturbance at x at time t, it would have been disturbance at x equal to 0 at a time t minus x over v. This is another way of describing the wave phenomena. If travel is to the right. On the other hand, if the disturbance travels to the left, then at x t, what I see is something that would have occurred at x equal to 0 at time t plus x over v, x is less than 0. So, it is traveling to the left. So, I can also describe a wave as a function of t plus x over v or a function of t minus x over v, and I will just show by arrows minus x over v is traveling to the right, plus x over v is traveling to the left, which is pretty much the same as writing it as x minus v t and t minus x plus v t, because a function f of t plus x over v is same as a function of v t plus x over v, which is a function of x plus v t. Remember, the variables are x and t. So, v I can take as a constant, and similarly function t minus x over v is a function of v t minus x over v, which is same as a function of v t minus x, v is a constant. So, I can write the wave disturbance traveling to the left or to the right as x plus v t, or a function of x minus v t, or a function of t minus x over v, or a function of t plus x over v. So, let us write that. So, a wave can be described as a function of x plus v t, a function of x minus v t, or a function of t plus x over v, or a function of t minus x over v. So, all these forms exist, and these are all traveling waves. So, let us see an example. All you have seen is how do I generate y x t equals a sine 2 pi x over lambda minus f t. This is what you have seen. You have seen earlier a wave which is a disturbance like this, and it travels. I will come to that in a minute, but before that I again want to go back and discuss that these functions f of x minus v t or f x plus v t, all these are functions of x and t both. So, a traveling or a standing wave is a function of x and t, that is the position and time both. So, if you want to visualize it, you can either look at f x minus v t as a function of time by looking at a fixed position, let us say x 0. So, what do? I stand at one point and see as a function of time how does the disturbance occur, how does it change with time. So, I stand at x naught and see how wave disturbance is changing with time. Or what I can do is fix a t equals t 0 and observe how the disturbance looks as a function of x. What would I do for that? Just take a photograph of the wave at that point, and then you can just see that as a function of x, you will see that it is spread, all right, and it is at a particular time, let us say t 0. At a slightly later time, it could be spread, but somewhere else. It would have travelled by a distance v t, or could have traveled to the left a distance v t, undistorted. So, this is how I would look at a wave phenomena at a given time, and at a given position if I stand there I will just see that things are just moving up or down or left or right depending on what kind of wave it is, and we will see how it changes with time. Now, let us see, I said earlier that how is this wave generated, right. So, A sin 2 pi x over lambda minus f t. So, suppose I fix my position, what do I see? If I stand at a particular point, then f at say x equal 0 as a function of time would look like a sine of 2 pi x is 0 over lambda minus f t, which is a sine 2 pi f t with a minus sign. So, I can write this as minus a sine of omega t. So, as a function of time I will just see that point at x equals 0 going up and down. What about as a function of position? As a function of position, if I take a snapshot at a particular time, this is what I am going to see, that this is spread from left to right all over, and let us say the time equals 0, then it will look like f x at time t equal to 0 is equal to a sine of 2 pi over lambda x. Naturally, what you see now is that if x goes to x plus lambda, you get a sine 2 pi over lambda x plus lambda, which is again a sine 2 pi over lambda x plus 2 pi, which is same as a sine 2 pi over lambda x. So, after a distance lambda, the displacement is the same. So, the lambda, which is the distance between two similar points, because the displacement is the same. I am showing this in pink. This lambda is called the wavelength. So, what I have shown you is that if I have this wave and I will just take a portion of it, this has wavelength lambda between two similar points, then the distance between two similar points is lambda, and after a certain time t, it would have moved further. So, I will just make it this distance would now be v delta t after time delta t. Now, the next question I ask through this is, how are lambda, v and frequency f of the wave related? So, let us try to answer that question. I told you if I stand at a particular point x equal to 0 or x equals some other point x 0, as a function of time this fellow is going to go up and down, which goes as a sine of omega t. So, after time t equals capital T, which is related to the frequency as 1 over f, the displacement is the same. Now, let us see if I took this wave frozen in time and looked at it after time capital T, it will look exactly the same, except If there was a point A here, this would have moved to point A at this point by distance lambda. So, in time t, the wave has moved by distance lambda. Otherwise, the displacement would not look the same. So, if it looks the same, it must have moved by distance lambda. So, v is going to be lambda by t, which is going to be f times lambda. This is a relationship you very well know. So, the speed of wave is given by f times lambda, this particular wave, which is known as the sinusoidal wave. Since we are talking about dispersionless waves, the speed is the same for all frequencies. How to generate a wave like a sine 2 pi x over lambda minus f t. So, let us look at that. I am now focusing specifically on this wave, what is called as the sine wave. So, this is called sine wave. So, let us see, if I have a string, an extended string, and I start shaking this point up and down as a sine of omega t, so that time period is 2 pi over omega, which is equal to t. Then, as we had argued earlier, so right now at y at x equal to 0 as a function of time is equal to a sine of 2 pi f t. Then y as a function of x and time would be y at x equal to 0 at time t minus x over v if it is travelling to the right, and that I know is going to be a sine 2 pi f t minus x over v, which is equal to a sine 2 pi f t minus x f over v. And we have just seen the relationship that v equals f lambda. So, I can write this as minus a sine of 2 pi x over lambda minus f t, which is the same form that you have been seeing or which I showed you earlier. So, if I take a rope, start shaking it at one end with a sine omega t, I create a sine wave which is travelling to the right. If I did this disturbance and the wave travelled to the left, then I would have y x t equals y at x equals 0 t plus x over v, and this would be a sine 2 pi f t plus x over v, which is same as a sine 2 pi f t plus x over lambda. So, these are different forms that you have seen. So, let me kind of summarize what we have done so far is that number 1, we have looked at a disturbance travelling with speed v and undistorted, and therefore, we could represent this as f x minus v t or f of t minus x over v if it travels to the right. that means positive x axis, and it is represented as f x plus v t or f of t plus x over v if traveling to the left. So, we have seen both ways, all right, and then we specialize to sinusoidal wave which is given as a y x t as amplitude a sine of x over lambda minus f t times 2 pi. So, it keeps repeating at along the x axis, it keeps repeating at intervals of lambda. In time at a fixed point, the displacement keeps repeating itself in with frequency f in time 1 over f. And the way this is generated is by shaking at one point with a given frequency in a simple harmonic manner. So that the wave created is something like this and it is traveling either to the right or to the left. We have also seen in this case that the speed v of the wave is given as the frequency times lambda, which can also be written as 2 pi frequency times lambda over 2 pi. This I can write as omega, and now I am introducing a new quantity 2 pi over lambda equals k, which is known as the wave vector or wave number. 2 pi over lambda is that many waves in 2 pi interval. So, omega over k. So, omega equals v k. That is a new relationship I am giving you, and in terms of this new relationship y x t can also be written as a sine of k x minus omega t. This is another form you will see in your books or places where waves are discussed. So, once we have understood this, now let me give you two kinds of waves. Known as number 1 transverse waves. These are waves where displacement y x t is perpendicular to the travel direction. So, examples would be waves on a string or example of transverse waves. The other kind is longitudinal, in which if the wave is traveling in the x direction, the disturbance is also along the same direction. So, in this the disturbance is in the same direction as the direction of motion of wave. For example, sound wave where I create a pressure difference, that is the disturbance, is an example of this. So, sound wave or longitudinal, where the pressure is actually in the same direction as the propagation of wave. One question we had asked in the beginning and I am going to address it now. Question: do waves carry particles as they travel? And the answer is no. I had argued it earlier. You can also see it on a string. If you just shake it, the string does not move from one place to the other, the disturbance does. if there is a water wave going, you can leave a leaf or a piece of paper there and you will see it just moving up and down, but it does not move with the wave. So, waves do not carry particles as they move. So, they do not carry particles, and also I can write, do they carry material, and they do not. Question number 2, do waves carry energy from one place to another? And the answer to this is yes. The simplest possible way I can answer this is, when I am speaking to somebody, the person hears. Whatever disturbance I have created, whatever pressure difference I have created, whatever movement, local movement of particles I have created by speaking, travels to the other place, creates the same disturbance on the eardrum or in the ears. That means it has the capability of taking that energy from one place and transferring it to another place. So, yes, waves do carry energy from one place to other. Third question, how do I calculate speed of waves? And this is a question which I am going to address now. So, let us first calculate the speed of waves on a string. For this, let us take a string and give it a disturbance. Let us say this is the disturbance, a sine wave, right. And so, let us say that y x t is given as a sine k x minus omega t. And I know, which I have said earlier, that v, the speed, is omega over k, or omega equals v k. I am going to need this. Now, let us see, as a particular portion of this goes up and down, what happens. So, if I take a particular piece of this string and assume, so let us write on the side, assume that y is much less than lambda. This is tight. So, at a given time, I have taken this snapshot, I have taken a picture of this. This feels a tension T to the right and a tension T to the left. Now, this angle that it makes with the horizontal is very small. So, let us call this theta here and theta here. Let us call this theta 1 at point 1 and theta 2 at point 2. So, we are going to say that theta is much less than 1, implies sin theta equals tan theta equals dy by dx for this given curve at this time, and cos theta is approximately equal to 1. So, now this tension T at position 2 has two components, one going up, one going to the right. This is T cos theta, which is roughly equal to T. Moving up is this T sin theta, which is roughly equal to T dy by dx at point 2. On the lower side, at point 1, this is tension T. It has a horizontal component and a vertical component. The horizontal component again is given by T cosine of theta 1, which is roughly same as T, and T sin theta 1 in the vertical direction, which is T dy by dx at 1. So, on this section between point 1 and point 2, I have net vertical force in the y direction, which is T dy by dx at this given time, dy by dx at 2 minus T dy by dx at 1 in the y direction and 0 in the x direction. Let us say this distance between 1 and 2 is delta x. Then by Taylor's theorem, or by simply taking derivatives, I can write dy by dx at 2 is equal to dy by dx at 0.1 plus take the derivative of dy by dx, which will be d2y by dx square delta x. Therefore, the vertical force on the section of this string is T d2y by dx square delta x. What would this force do? It will make it accelerate up or down. So, if I equate this to the acceleration, let us see what happens. So, acceleration of this section is going to be nothing but I will freeze at that particular point at x and see it moving up and down. So, at that given position I will calculate dy by dt square, that is the acceleration. So, the force which is T d2y by dx square at this given time, which is also written as, and I will just use a technical term, the partial derivative of y with respect to x, because y is a function of both x and t. By writing partial, I mean t is kept fixed, and the acceleration is d2y by dt square at this position, which is also written as partial derivative of y with respect to t. This automatically means it is a given x, and the relationship between the two is going to be force equals mass of the string mu delta x times acceleration. Where mu is mass per unit length of string. So, I get T d2y by dx square at that fixed time is equal to mu delta x, there is a delta x here, there is a delta x on top, d2y by dt square at fixed x. Now, let us take y x t equals a sin k x minus omega t. Then what do we get? So, what we have written is that T d2y by dx square, which correctly actually I should write as a partial derivative, times delta x is equal to mu delta x d2y by dt square at a given x. Delta x cancels, and this is the equation, and I am taking a sinusoidal wave. So, y equals a sin k x minus omega t d2y by dx square for a fixed time is going to be minus k square a sin of k x minus omega t, and d2y over dt square at a fixed x is going to be minus omega square a sin of k x minus omega t, and I substitute it back in this equation, and I get t k square is equal to mu omega square, and this gives me omega over k is equal to square root of t over mu. Recall what we had said earlier. Earlier I had said that V equals omega over k, and this we have calculated to be root t over mu. So, you see how taking Newton's equation of motion for a particular section and relating how omega and k should be related to the speed of wave that we did earlier, although for a sinusoidal wave, we could get what the speed of wave should be in terms of t and mu. So, this also implies that wavelength for a given frequency will be v over f, which will be 1 over f square root of t over mu. So, this is the derivation that we have done just by simply looking at how Newton's equations are applied for a section of wave. Another example I am going to take calculation of speed of waves is the sound waves. In this, what we do is, suppose I have a air column where I take a particular section, let us say of length delta x, and create an extra pressure P at this point. So, when I am speaking, for example, I create a pressure and this pressure changes with distance. So, it becomes P plus delta P on the next side. In creating this pressure, I have also moved this wall by a distance, let us say z, and therefore, here on the other side it moves by z plus delta z. So, let me look at this shaded portion of air and look at this point which I am showing by arrow, and I will see the movement of this whole shaded section as a whole and relate it, calculate its acceleration related to the force that it is feeling. Now, let us see the force it feels. So, if I look at this portion, there is P plus delta P on this side, P on this side. So, if this cross sectional area is A, then the force it feels is to the left, which is delta P times area. And what would this force do? This force would give it an acceleration. So, we are going to write that d2 z by dt square at this point x, let us say this point is x, times the mass of this portion, shaded portion, is going to be equal to minus delta P times A. From this, I should be able to get the speed of the wave. Now, what does this pressure also do? So, this delta P, the pressure difference, makes it accelerate. On the other hand, the pressure P on both sides changes the volume. Through that volume change, I can actually relate delta P to some other property of this gas, and let us do that. So, in this gas or in this air, I have this small portion on which pressure P is here, pressure P plus delta P is here, the length is delta x. I am looking at point z, and what we have seen is that mass, which is going to be the density of this air times its volume A delta x, then acceleration we have figured out is d2f by dt square. Then we have seen that the delta P times A is the force, and therefore, we get rho delta x is equal to rho delta x times the acceleration d2f by dt square is equal to minus delta P times A. There is an A also on the left hand side, and this gets cancelled and you get rho times d2f by dt square is equal to minus delta p over delta x. Let us see how do we calculate this delta p over delta x. So, pressure P changes the volume. Mind you, this pressure P is not the existing ambience pressure, it is the extra pressure that I am creating. So, that is why this changes the volume. How much does it change? So, I know that the bulk modulus is equal to minus V dP over dV, or minus V whatever extra pressure I am applying and how much is the change in the, I am calling it delta P bar over delta V. So, delta P bar is the pressure, delta P bar is not the delta P that I am taking, is the pressure that I am applying. Delta V is going to be equal to initial volume is A delta x. The point on the left moves by z, point on the right moves by z plus delta z. So, delta V is going to be A z plus delta z minus A z, which is nothing but A delta z, which is nothing but a change in z as a function of x times delta x, that is the change in the volume. So, therefore, I am going to have P over this change delta V times V of this shaded area is equal to B is equal to minus V is A delta x times pressure P divided by delta V, which is A dz by dx delta x. Delta x and delta x cancels, A and A cancels, and I get therefore P is equal to minus B dz over dx. So, what we have found is that rho d2f by dt square is equal to minus delta p over delta x, which is like minus dp over dx, and we have found that p is nothing but equal to minus b dz over dx. What is z? Z is the displacement of this. What is f? F is also displacement of this left hand portion. So, f is same as z, which is giving me the acceleration of the body. So, I am going to have rho d2z over dt square is equal to minus dp over dx. Again, this is no time. So, this is partial derivative, which I can write now as plus b d2 z over dx square, and where did I get this from? This I got from here. So, I have d2 z over dx square is equal to rho over b d2 z over dt square, or d2 z over dt square is equal to b over rho d2 z over dx square. This is the equation we have got. Now, what we saw earlier is that p is proportional to z. So, I could also have written this in terms of p, but this is what it is. The displacement that we create by changing p follows this equation, and again taking sinusoidal wave, that means I am taking z x t to be a sine k x minus omega t, I get d2z by dx square at a fixed time to be equal to minus a k square sine of k x minus omega t and d2z over dt square at a fixed x to be minus omega square a sine of k x minus omega t, and substituting these in the equation, I get d2 f or d2 f over dt square, which is the same as d2 z over dt square equals b over rho d2 z over dx square, or minus omega square equals b over rho times k square, or omega square over k square, which is nothing but v square equals b over rho, implies speed of waves is square root of b over rho. This is a well known result. Now, b is the bulk modulus, and what has been argued is that at high frequencies this is the adiabatic bulk modulus, because when there is a high frequency wave passing through, there is not enough time for the heat to dissipate. So, it is not constant temperature, but adiabatic bulk modulus. So, what we obtain now for that V for air or a material is square root of B over rho. So, let me just conclude this second portion by saying that we introduced the sinusoidal waves, then calculated speed of wave by relating acceleration of a portion of medium, and we considered string and bulk medium for sound waves, relating acceleration of portion of medium to the force generated due to wave disturbance. In the next coming lectures, we will now explore these concepts related to waves further.